Okay, here's a little video lesson on friction and some questions on page 128 associated with that. So, you know that if you are pushing on a box and moving it, you have to push on the box. And so while that may seem obvious, it's interesting to think about why you have to push, okay? So, for example, imagine you are sliding a couch across the floor, okay? F equals ma, or Newton's second law, says that if you are moving it at a constant speed, acceleration is zero. Zero. Meaning the force would then be zero, and you wouldn't have to push. But you know from reality that when you push on a couch, even if it's just moving at a constant speed, you still have to keep pushing. That is because friction between the ground and the couch pushes back. So imagine you're pushing this couch across the floor, and all of a sudden your good friend comes and sits on the couch as you're pushing it across the floor and says, ha, 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 okay? Intuitively, I'm sure you understand that you would have to then push with a greater force. So, what's going on with friction? Well, if we look over here, this is sort of a microscopic. So imagine you're zooming. Let's see. Imagine you're zooming in, look at all those pixels, okay, to right here where the couch actually has this little support that touches the ground, okay, and then you zoom in 1,000 times more. And what you'd actually see is that on the sort of microscopic and definitely molecular level, you'd have this type of situation where the surfaces are not smooth, they're jagged, and so you get this sort of the hill and the valley sticking together. There's also sort of an electrostatic attraction. Sometimes it happens between two surfaces. So this is why things stick together. This is what causes friction at the really small scale. And so when you have a surface that is wet or greased up with grease or whatever, what happens is it provides sort of a buffer in between. And so this would be filled with the fluid or something which is sort of easy to move around, and it inhibits the two surfaces from actually getting super close to one another. So this surface could kind of glide along the water and not really come into contact with the surface. Okay. So, of course, we're going to calculate friction, and this is the way it works. We have talked about the term normal force. So normal in math and technical fields refers to perpendicular. So I'll draw a little perpendicular sign there, perpendicular. So it is the force perpendicular to the surface. In this case, we have you pushing, and here's your good friend, right? The normal force would be in this direction. I'm going to draw that. Normal force would be like this. Okay. It is the force of the ground on the object that is experiencing friction. Frictional force, on the other hand, is the force between the two surfaces that opposes relative motion. What? That opposes relative motion, meaning if this surface is going this way and this surface is going this way, right, when one slides across the other, that means they are moving relative to one another, and friction opposes that motion. And then this cute little guy here is called mu. You could spell that mu. And that is the coefficient of friction between the two surfaces, and different stuff has different coefficients of friction, obviously. Your shoes on pavement are pretty sticky, so there's a high coefficient of friction. Your shoes on the ice skating rink are pretty slippery, and so have a low coefficient of friction. If a surface were completely frictionless, the coefficient of friction would be 0. So up here we could write something like mu is going to be greater than 0. It's really basically kind of impossible to have a completely frictionless surface. And then this isn't actually true, but it's kind of true. it's rare to experience a coefficient of friction that is more than 1. Okay, 1 is super, super sticky. Okay, like you find some climbing shoes, right, and put those on the stickiest form of granite, or race car tires, on a hot surface or something like that. So these are the values we expect for coefficient of friction, approximately. Okay, and this is our formula. Okay, so we have the force of friction equals the coefficient of friction times the normal force. And hopefully it's intuitive, hopefully it makes sense to you that the friction is going to increase when your friend sits on the couch. So when your friend sits on the couch, what it's doing is it's increasing the force downward, okay, the weight, which would be balanced out by the normal force, F sub n. So if this increases, and you say, aha. All right, and lastly, actually, not lastly, in addition, static versus kinetic. So there are two different types of friction. Static friction refers to when the surfaces are not moving relative to one another, and kinetic friction is when they are moving relative to one another. So in the example of an automobile, so we just had some snow and people were talking about how scary it was to drive in four-wheel drive or snow or ice or whatever. I just got some snow tires for my car. What am I trying to say? Here's what I'm trying to say. Here's the road, here's the tire, okay? So if you are on an icy road and you slam on the brakes, all of a sudden, the tire is moving this way relative to the road, okay? And it is now slipping on the road, and the friction that it experiences will actually be less than if it is rolling. Because if it's rolling along the road, then you have this little section in contact with this part of the road, this little section in contact with this part of the road, this little section in contact with this part of the road, and the tire actually doesn't slip on the road and you get more friction. So this is why anti-lock brakes are a good thing, is that they keep your tire rolling so that the two surfaces are not moving relative to one another. In addition, you can steer. I know I'm going through this quickly, but we'll talk more about it. This is just an introduction. So anyway, the coefficient of static friction is usually greater than the coefficient of kinetic friction by a slight amount. Okay, and then almost lastly, if you look at this formula, it's like, all right, so here's the force of friction, and it depends on, the force that we push the two surfaces together with, obviously, and then the type of surfaces that they are, but it doesn't depend on the area that's in contact. What? And that's sort of counterintuitive. So pretend this is a surface, and we have, this is within my artistic abilities, this is the same box, okay? It's just lying on different sides. So we have the small side, we have the medium side, and then the big area side. So pretend this is the same box, it's just lying on the ground in different configurations. So it has the same mass in all situations. Only here the area in contact is great, and here the area is medium, and here the area in contact is very small. So when we pull, you kind of think that this area, because it's greater, is going to produce more friction, yet it doesn't. Okay, so it's more the pressure. Think about the pressure between the two surfaces. So like, because it has the same mass, it's the same force downward, the same weight. Okay, and so this has the same weight, and it is distributed over a smaller area, so there's more friction per area here. Here, because the weight is distributed over a larger area, there's less friction per area. But because there's more area, the actual frictional force ends up being the same. So I would write friction and friction and friction, indicating that even though we have less area here, because we have the same weight, there'd be more force per area creating more friction per area for less area. I know that's a lot of words, but the bottom line is that the actual area in contact doesn't really matter. The frictional force will be the same. This is what our physics tells us. It's only the force pushing the two surfaces together, not the amount of area that is in contact between the two surfaces. Now that's counterintuitive because we see this was my race car over here, and then this was my normal car, or whatever. And when you see race cars or sports cars, they've got these wide tires, and you see, you know, a little Honda Civic, and it has skinny tires, and you think, well, the wide tire provides more friction. Yet, what the physics is telling us is that, what the physics is telling us is that the area in contact doesn't really matter. But that's sort of an idealization. And when you're talking about race cars, there are many factors involved in how they stick to the road, but the wide tires do help with the sports car, okay? And there are a number of reasons for that we could get into later. Just know that this works for simple situations where they're not going fast and they're not, you know, maybe the forces involved aren't large and that kind of thing. Okay. So next is some questions. I'm going to work through this one, and then you're going to do these, and then I'm going to show you solutions to these. So it goes like this. Question 17. Girl exerts a 36 Newton horizontal force as she pulls a 52 Newton sled across a cement sidewalk at a constant speed. So I would draw a diagram. Here's my sled, and I would write 52 newtons in there. So that's not the mass of the sled, that's the weight of the sled. If it were the mass of the sled, it would have been given to us in grams or kilograms. We're told that the girl pulls with a force of 36 newtons, and that, this is sort of key right here, constant speed, okay? And then we're looking for coefficient of friction. So because she pulls at a constant speed, it means the forces on the sled are balanced. So if we were drawing a free body diagram, we would know that the force of friction in the backwards direction is 36 newtons. Okay, this is because it's a constant speed. If it were accelerating forward, this force would be greater than the frictional force, but it's not. We're starting simple. So we know that the frictional force is 36 newtons. We know that the normal force will be balanced out with the weight. So I could draw this weight and this normal force. Now, how do I know that those forces are balanced? Well, if they weren't, the sled would be accelerating upward, like Santa's sleigh, or downward, I don't know, the devil's sleigh or whatever. So it's not. It's going in a horizontal direction, so the vertical forces have to be balanced. And we know that the normal force will then be equal to the weight, which was given to us 52 newtons. Let's plug in. Force of friction equals mu times the normal force. We know that the force of friction is 36 newtons. We know we are looking for mu, and the normal force is the weight, 52 newtons. Is the normal force always the weight? If it's a flat surface, yes. If it's a slanted surface, no. We'll do more with that. Don't you worry. After dividing, let's see, calculator says 36 divided by 52 equals 0.69. Okay. So mu is 0.69. Does that make sense? Well, sure. It's between 0 and 1. If I got something like 500, I'd say, yeah, I'm probably wrong. If I got something like negative 0.69, I would say, yeah, I'm definitely wrong. A negative coefficient of friction will negative exist. Never exist. Haha. Bunch of stupid jokes in this video lesson. I hope you're laughing at my expense. Okay, lastly, I want you to now solve, we're on page 128. Oh wait, it's right here. Okay. Haha, that was pretty funny. I want you to solve these. So put this on pause, solve those, see what you get, and then push play, turn the page, and let's take a look at the solutions. Alright, so if you didn't push pause and solve these, shame on you. Alright, here are the solutions to 18, 19, and 20. Oh, and 21. I think this is enough explanation. So check your work. If you didn't get them, write down the correct solution, think about it. Hopefully this has been a good learning experience. Thank you.